All right, let's dive into a real chemical head scratcher today. We're talking about a puzzle that really stumped early chemists and shows us exactly why our simplest models sometimes just don't cut it. We are going to solve the mystery of oxygen's weird magnetism.
So get this, you take liquid oxygen, this really cool pale blue liquid, and you pour it between the poles of a super strong magnet. Now, you'd expect it to just fall right through, right? But it doesn't. It actually gets stuck. It just hangs there in midair, defying gravity, held by some invisible force. This is what's known as paramagnetism, and it's the central clue in our mystery today. So what on earth is going on?
And this is where it gets really interesting, because there's a huge conflict here. If you draw a normal Lewis structure for an oxygen molecule, following all the rules from Chemistry 101, it shows that every single electron is paired up nice and neat. That model predicts that oxygen should be diamagnetic, meaning it should actually be slightly repelled by a magnet. But as we just saw, reality tells a totally different story. Experiments prove O2 has two unpaired electrons, which is what makes it paramagnetic. Our simple model says one thing, but reality says the complete opposite.
So, what happens when your theory breaks? Well, you find a better one. And in this case, that new, more powerful tool is called molecular orbital theory. It's a much more sophisticated way to look at how atoms bond together, and it's not only going to solve our oxygen puzzle, but it's going to unlock a whole lot more. The biggest change you have to make in your head with MO theory is this. Just forget the idea that an electron belongs to a single atom. It's not like they're just orbiting one nucleus. Instead, I want you to imagine that the electrons exist in these new orbitals that stretch across the entire molecule. They're basically shared property of the whole system. It's a totally different way of thinking about a chemical bond. Now, to really get how these new molecular orbitals are made, we have to embrace a little bit of the weirdness of quantum mechanics and think about electrons as waves. So when the electron waves from two separate atoms get close, they can interact or interfere, just like ripples on a pond. And this interference can happen in two main ways. Over here on the left, you've got constructive interference. See how the peaks line up with peaks and the troughs line up with troughs? They add together to make a bigger, stronger wave. But on the right, you've got destructive interference. A peak lines up with a trough and, poof, they completely cancel each other out, creating this flat line or a node. So when atomic orbitals combine in that constructive, additive way, they form what we call a bonding molecular orbital. All that electron density gets concentrated right between the two positive nuclei, and it acts like an electronic glue, holding the whole thing together. This is a super stable, low-energy state, and that, right there, is what a chemical bond really is. But here's the thing, for every bonding combination, you also get an anti-bonding one. When atomic orbitals combine destructively, they create an anti-bonding molecular orbital. You can always spot it by that little asterisk. In this case, that node forms right between the nuclei. There's zero electron density there. The electrons are pushed to the outside, and that actually starts to pull the nuclei apart. This is a high-energy, totally unstable situation. Okay, so we've got these two new kinds of orbitals, stable bonding ones and unstable anti-bonding ones at different energy levels. To keep track of all this, chemists use a really simple but incredibly powerful tool, the molecular orbital diagram. You can just think of it like an energy ladder that tells us where all the electrons in the molecule live. Now, filling one of these diagrams just follows a few simple rules. First, you count up all the valence electrons. Those are the outer ones that do all the work. Then, you start filling the diagram from the very bottom, the lowest energy level, and work your way up. Now, if you hit a level with multiple orbitals at the same energy, Hund's rule says you have to put one electron in each before you can double any of them up. And finally, remember that any single orbital can only hold two electrons, max, and they have to have opposite spins. Once the diagram is all filled in, we can calculate something called the bond order. The formula is super easy. It's just the number of electrons in those stable bonding orbitals minus the number of electrons in the unstable anti-bonding ones, all divided by 2. And this little number tells you everything. A bond order of 1 is a single bond. 2 is a double bond. And if you get a bond order of 0, that means no stable bond can form. The molecule just falls apart. Let's try a quick warm-up. Take H2, a hydrogen molecule. It has 2 valence electrons total. So they both go into that low-energy bonding orbital. The bond order is 2 minus 0 divided by 2, which equals 1. A stable single bond, exactly what we expect.
Okay, now what about dihelium, He2? It's got 4 electrons. The first 2 go in the bonding orbital, but the next 2 are forced up into that high-energy anti-bonding orbital. The bond order is 2 minus 2 divided by 2, which is 0. The theory perfectly predicts that dihelium shouldn't exist as a stable molecule. Pretty cool, huh? All right, we've got the rules down. We've seen it work for the simple stuff. It's time. Let's go back to our original problem and build the molecular orbital diagram for dioxygen, O2. So each oxygen atom brings 6 valence electrons, giving us 12 total to place in our diagram. We start at the bottom and work our way up. 2 electrons go in the sigma bonding, 2 go in its anti-bonding partner, then 6 more fill up the next set of bonding orbitals. So far we've placed 10 electrons. We only have 2 left. They have to go into the next level, the pi star anti-bonding orbitals. And here is the key moment. Remember Hund's rule? Since these 2 orbitals have the exact same energy, the electrons don't pair up. No, 1 electron goes into the first orbital, and the last one goes into the second.
And there it is. Look at that. The finished diagram, built from the rules of quantum mechanics, predicts that a molecule of oxygen must have exactly 2 unpaired electrons.
This is the solution to our whole puzzle. It's those 2 lonely electrons sitting by themselves in those anti-bonding orbitals that act like tiny little magnets. They're the reason the whole molecule gets pulled into a magnetic field. Molecular orbital theory perfectly explains the experimental fact that our simple loose structure just couldn't handle. Mystery solved. And what's really elegant about this is that the whole theory is self-consistent. If we go ahead and calculate the bond order for oxygen, we've got 8 electrons in bonding orbitals and 4 in anti-bonding. So 8 minus 4 is 4, divided by 2, gives us a bond order of 2. That perfectly matches the double bond that our simple Lewis structure predicted. So you see, MO theory doesn't throw out the old models. It adds a much deeper, more accurate layer on top. But the real power of this idea goes way beyond explaining just one quirky molecule. This exact same framework lets us predict the properties of all kinds of other molecules. And when you scale it way up, it even explains how solid materials work. I mean, just look at the other molecules in the same row of the periodic table. MO theory correctly predicts that nitrogen, N2, has a bond order of 3, a super strong triple bond. It predicts O2 has a double bond, and fluorine, F2, has a single bond. And just like with helium, it tells us that neon, Ne2, with a bond order of 0, shouldn't exist as a stable molecule. Every single prediction matches reality perfectly. So what happens when you take this idea to the extreme? Instead of just 2 atoms, what if you have trillions and trillions of them, all packed together in a solid crystal? Well, you get countless bonding and anti-bonding orbitals that are so close in energy that they just blur together, forming these continuous energy bands.
The filled low-energy orbitals form what's called the valence band, and the empty high-energy orbitals form the conduction band. And the energy difference between them, the band gap, that's what determines a material's electrical properties. In a conductor, like a metal, that gap is tiny or doesn't exist at all, so electrons can just jump across and flow freely. In an insulator like glass, the gap is massive and the electrons are completely stuck. And right in the middle, you have the most important materials of all, semiconductors.
And this right here is why all of this matters so much. This scaled-up version of MO theory, which we called band theory, is the fundamental science behind every semiconductor on the planet. It's the reason we can design the silicon chips that power our computers and our phones. It's how solar cells work. In fact, the very screen you're watching this on right now exists because we understand how these atomic orbitals combine on a massive scale. So it started with a simple, weird observation: liquid oxygen sticking to a magnet. And that forced us to find a more powerful theory. And that new theory not only solved our little puzzle, but it ended up explaining the foundation of all modern electronics. It really makes you wonder, doesn't it? What other invisible quantum rules are out there, shaping the world all around us, just waiting for us to discover them?